Today I'm joining Asta Agrawal to talk about harnessing Coral and Iceberg for advanced incremental view maintenance. But before jumping into the details of the user experience we're going to talk about today, let's take a look at the scene of the data lakes today. So data lakes are characterized by leveraging a variety of compute engines, such as Spark, for example, which is an engine for big data analytics with multiple query APIs, such as SQL and Scala. Reno is another big data engine for analytics as well as interactive querying, which uses SQL APIs for the most part. Flink is another engine, and it's kind of having like use cases in both streaming and batch, and typically using convergence use cases between streaming and batch, as well as some orchestrators that users typically use for scheduling jobs that happen through those engines. Those orchestrators include Apache Airflow and Jupyter. And this data scheduling or data job scheduling happens either on a regular basis or on a schedule or based on data availability. In addition to those, there are also ETL tools such as DBT, which are typically used to implement, test, and build data workflows. In addition to the tables that exist in the data lake, which are used as the source of the input to compute insights on top of them, leading into other tables as well that keep being generated within the data lake. Even tables themselves have a variety of formats and ways to structure them. So Hive tables have been the de facto table format for years until modern table formats such as Iceberg came along. We've seen also other table formats in data lakes such as Delta tables and Hoodie tables, which kind of abstract also low-level file storage details such as the file formats, and those include things like Avro, ORC, and Parquet. On the other hand, there are other data source types such as views, which can be expressed on top of tables to express like kind of shareable and reusable logic that can be used also and queried from those compute engines, and those leverage different query languages and UDF APIs to express that logic. So far we've been talking about the diversity of tools and technologies that are being used in data lakes, but the other important dimension as well is magnitude. So in modern data lakes, data keeps growing as more usage is adapted by the tool or the utility that's provided by the company or the application, and data keeps growing. And that logic that we talked about continues to grow as well. And as it grows, more data insights need to be made on a daily basis or a recurring basis, scanning the data again and again. So, and it's also not about scanning data only, but also about recomputing and passing those records through the entire compute logic repeatedly to continue to deliver those insights. So to address those issues related to diversity of technologies that are used in data lakes, as well as the growth in data, and maybe make users more productive and as well as making the systems more efficient, we propose like a new user experience for automatically maintaining data and compute incrementally. So what that means is instead of computing the data repeatedly on the same input, basically we can compute the insights based on new data only. So that leads to lower compute cost in addition to lower latency, because now that we can get insights faster, we can do them more frequently and get like more up-to-date information. And at the same time, that improves the user experience, because users now do not need to focus on the variety of tools that they need to use or their APIs, or maybe think about the incremental maintenance logic as well. or the mechanics of it, but just focus on writing the logic in the way that we think about it in terms of like the implementing the business objective of that. And with that, like users can build like full DAGs, which is directed acyclic data graphs, using just SQL. So the key components that we introduce into this like user experience to make it happen are two things. Basically, we leverage Iceberg for its capability of providing asset guarantees and consequently snapshot APIs and incremental scans. And we leverage Coral for its ability to express logic and model it in an abstract way through an intermediate representation, and then rewrite that logic to an incremental version of the original logic. So we're going to see more details about this throughout the slides. And we present the end-to-end user experience also through a case study using DBT. And since DBT is the user-facing tool here, let's take a quick look on what DBT is. So DBT is an open-source data transformation tool that enables teams to quickly build complex data pipelines, and DBT is quite configurable to be connected maybe to multiple BI tools or multiple compute engines, and have users like pick and choose what they want in terms of like how to compute and how to present the data. But DBT, for the most part, helps them to author their like data logic and data application, and have it maybe reviewed by their team and then maintained and so on. So one key concept in DBT is the materialization mode. So basically, users build a model, which is presented here on the right-hand side as like a file, a SQL file that contains their select statements. And the model or the materialization concept that is the topic of this slide basically allows the user to have this query written to another output table according to hints that are provided in that materialization mode. So the materialization mode that is most commonly used is called table, which basically takes the query and then dumps its output to an output table. So now if the underlying data change in the input tables, the model needs to be run again, and then the output table needs to be regenerated. And in this case, as you could expect, a full scan happen and a full recompute happens every time we want to refresh the output table. So DBT does provide another mode that is called incremental, but in this mode, the thinking and design of incremental compute is left to the user, where they use like annotations like the one we see here on the screen. And they have to kind of break down their logic into pieces. One piece maybe that's related to the batch compute, and then one piece that is related to incremental, and then depend on predicates like timestamp, and figure out like when new data arrived and correlate that with tuples in the records, in their tables, and then like write their logic in a way that can consume changes and compute based on those changes. And as designated in the official DBT documentation, this is suggested for advanced usage. So to summarize the expected user experience from the work we're discussing here, we're envisioning a user experience where users still like implement their logic using the mindset of the table materialization mode, where they just write the query as they think about it in terms of business logic, but then have a drop-in replacement for the table materialization mode, which is called incremental maintenance. And with that mode, users can write their logic in a batch way, but have it executed in the background using an incremental approach. And just to give you an idea about like how this way of having the user write their query in one way, but then have it executed in another way that's incremental, let's take a quick idea on what incremental query evaluation is. So let's drive it through this simple example where we have a join between two tables that are the inventory table and the prices table. And let's say that at T1, inventory had 2 records and prices had 1 record. Then we compute the result, let's say, in a batch mode for now, just to distinguish with the incremental method. So that produces one record. So let's say at T2, we have got new data in both tables, and we want to refresh the output table. And in this case, we would do the recompute again in the batch way, and then find that the output table contains 3 records. Let's move on to the incremental way. So the incremental way shares the first iteration with the batch way because we have to compute that anyways. So again, at T1, we still have that 1 record. Let's see what happens when we move on to T2. So at T2, new data arrives, and that is described or visualized here through the green records. So the gray records were the ones that existed before adding the new data. And those would be represented in the query with the same table name, but with the suffix _ delta. So in this case, if we want to find like what new data needs to be appended to the output, we would find that there is a join that needs to happen between the prices table or the new changes in the prices table, which is the green part on the right table, and the existing data in the inventory, which is the gray part. So that is basically the join between inventory and prices delta. So that's one piece of the new data that needs to be added to the output. The other piece is basically the other, like the corresponding join between the green part in inventory and the gray part in prices, which is represented in the query as inventory delta join with prices. So that produces another part of the join. In this case, it's empty, which is fine. Then the last part is finally joining the 2 green parts from both tables, which is inventory delta with prices delta, and this produces the delta T gamma. So like end to end, the final query result at T2 is basically whatever we had at T1 plus the 3 parts that we discussed, which are delta T alpha, delta T beta, and delta T gamma. And with combining all of those, we can refresh the output table only with the changes that arrive to the input tables without having to do a full refresh. And at the same time, like the compute itself can be expressed with another SQL query, which is functionally equivalent to recomputing everything from scratch, but by decomposing the statement into like the original select statement into 3 smaller select statements and unioning the output of them and adding the result to the initial table state at T1. So to understand how we achieve this using Coral, which is the query rewrite component that we use to achieve that rewrite, let's take a look at what Coral is as well. So Coral is a query rewrite engine that is comprised of 2 main components. One is the common representation that captures the logic in a query, and it can express SQL different dialects or different query plans or different ways to push down predicates from engines to data sources and so on. So the logic part is one core component, and it is used in a standardized way, which we're going to see throughout the rest of the slides. In addition to a number of adapters that transform an input representation, which could be in SQL or some other relational algebra language, to that common representation that we just talked about, as well as adapters to convert that common representation to another output representation, which again could be SQL or some relational algebra language. So to take a look at some of the supported languages or dialects as of today, on the input side, for example, Coral supports translating High SQL, Spark SQL, and Trino SQL, which is still work in progress, to the common representation, and again from that common representation to Hive, Spark, or Trino SQL. And one feature of having this common representation be kind of the contract in between the input and output is that allows us to add like future dialects on either side without having to correlate them with every dialect or output on the other side. So by just adding one dialect on one side, you get to translate that or convert it to the output on the other side, including, by the way, that the dialect itself, which is like the use case in this user experience where, for example, in incremental maintenance, we express the logic in one dialect, but also we have another kind of rewrite in the same dialect. So to look closer at Coral IR, it consists of two representations, and both are based on Apache calcite classes. And we're going to see that what that means here. So one representation is the abstract syntax tree representation, and that extends SQL node representation in calcite. And typical use cases for that are language translations between dialects and so on. And the other one is at the logical plan representation, and that extends calcite drill node classes. And typical use cases for that, as opposed to the abstract syntax tree representation, logical plans are typically used in query optimization or query rewrites, such as the use case with incremental rewrites and dynamic data masking. So just to get like a visual idea of how the IRs look like. So this is a depiction of the abstract syntax tree representation, and it is actually generated by a module in Coral that you can try out. And it would like print out or generate that kind of diagram, which is on the right-hand side of the image. And that represents those two queries that exist on the left-hand side. So one query is in Spark SQL, the other query is in Trino SQL, but then you could transform Spark SQL to that representation and back and forth, and in the same way you could do the same with Trino SQL. And keep or like note also that both queries express the same kind of semantic, but they are written differently and they use different operators to express the same semantics. And we use Coral IR to capture like the standardized semantics that both mean, and then we can convert back and forth between them. So this is the representation at the AST layer, and as you can see, it mostly captures like query tokens and not necessarily like full-fledged and well-defined operators. And the other representation, which is the logical plan, is the one that more captures the relational algebra and query operators nature of the common representation. And again, we can go from the languages on the left-hand side or the SQL on the left-hand side to the representation on the right-hand side. So just to recap, like what are the features of Coral IR that we've discussed so far? Basically, the fact that it's being used in production, and it can translate or like convert queries in hundreds of thousands of jobs. Both we use it inside LinkedIn and also outside as part of Trino translation of views from Hive to Trino. So like the kind of operators that are implemented in it are also quite expressive because it captures the operators from a variety of engines and in a standardized way. It is also multifunctional because it has those two IRs that we discussed, the AST and the logical plan IRs. It's also bijective because it can represent or like convert from the AST representation to the logical plan and back from the logical plan to the AST. It is translatable because one can go from language to AST to another language, or do the same pipeline but having the plan in between. It is rewritable because one can translate or like rewrite the AST to another AST that captures either like slightly different logic or maybe same logic but written in a different way, both at the abstract syntax tree level or the plan level. So we can rewrite both. So with combining all these kind of building blocks of conversions, we can build quite complex like logic rewrites. So with that, where I talked about the like user-facing experience through DBT and the underlying tech through Iceberg and Coral, I would like to hand over the presentation to Asta, who's going to talk about like putting everything together and demo the user experience through DBT, Coral, and Iceberg. Over to you, Asta.
Thank you, Walo. Can you see the slides?
Yeah, we can see your slides, yes.
Okay. Thank you. Yeah. So just as Vala mentioned that Coral allows you to interconvert between two representations or to go from an input representation to an output representation through an intermediate representation that we refer to as Coral IR. Let's take a closer look at how we can use the same technology to generate an incremental SQL version given an input SQL. Or more specifically, in our case, let's look back at the same example for join between the inventory and prices table to generate the incremental SQL on the right side. So the first step is to use a SQL to Coral IR converter, which allows us to represent this query as a Coral IR logical plan, where the top level node is the project rel node, where we are projecting two columns, followed by a join node, which represents the inner join between inventory and prices on the ID column. And the join is connected to two scan nodes representing the base tables, inventory and prices. The next step is to rewrite this logical plan to generate the incremental logical plan. So let's visit this logical plan on the left-hand side in a top-down manner. When we encounter a project node, we make no changes. But when we encounter a joint node, inner joining between two data sets, we convert that into a union of three joins, where each join is between the base table and the delta table. The base table here means the base representation at T1 timestamp, which has the older records, and the delta representation is the delta new records added to each table. So we perform a join, three joins, a join between the base table and the delta of the other table, the delta of the first table and the other base table, and the third join is between the two delta representations. We finally use a similar Coral IR to a SQL converter, which allows us to convert this logical plan, the incremental logical plan on the left-hand side, and output the corresponding SQL text representing the same logical plan. Now we have looked at the core Coral technology, which allows us to convert a query into its incremental query. But how does DBT actually interact with Coral? And for that, I want to introduce another component from within Coral that's called Coral Service. Coral Service is a Spring Boot service. This component exposes REST APIs that allow you to interact with Coral. It has multiple endpoints which allow you to convert the SQL across different dialects, and also exposes another endpoint, API incremental rewrite, where you can provide your input SQL and then output, get in return the incremental SQL representation for the same SQL. The Coral service you can interact with Coral service from the UI or an interactive CLI. So let's look at a CLI example for the same endpoint, where you can fire this post curl request, providing the query that you want to convert, and the base tables, in this case, inventory and prices that you're referring to. You're also expected to provide the language, which would be Spark in this case. And we fire this curl post request to the same endpoint. In response, we get the incremental SQL version, which is defined in terms of the base data sets, which is inventory, and the delta versions of the data set, which is the table underscore delta. It also returns the same base table names and the incremental data sets which are referenced in the incremental SQL. Taking a closer look at the SQL, we're again looking at the same SQL where we have the same projects, the product name and product ID, and the inner SQL is a union between three joins. We first do a union between the two joins where we are joining inventory with prices delta, union with a join between inventory delta and prices. The result of that is finally union with another join between inventory delta and prices delta. So now we have looked at how the DBT can interact with Coral using Coral service to finally generate the incremental SQL version. But there's still a couple of elements missing at this point. So let's look at the remaining interaction. So a quick recap for what DBT offers, which is the table materialization mode, where you would set up a script and provide the mode table, which would reapply, rerun your SQL over and again, dropping your expected output data set and recomputing it every time you execute your DBT model. And what we are looking and what we are offering is an incremental maintenance materialization mode, which would have a similar setup. But instead of doing a full recompute, it would allow for an incremental compute. Behind the scenes for an incremental maintenance materialization mode, it would make a post request to the Coral service endpoint to return an incremental representation for the same SQL. But we also need some additional post-processing logic so that we can actually make use of the incremental SQL that is returned by Coral. So let's look at what that post-processing logic looks like. And this is where we leverage Iceberg. So Iceberg is the high-performance table format, which allows us to time travel. And with this time traveling, we are able to identify records added to the base tables between two timestamps. And we'll see over the next slides how this is the key ingredient which enables us to incrementally maintain an output data set. So looking at the code generation, and let's use the inventory table as an example, as the same example. We have two timestamp. Let's say that till t now -1, we had the base version of the table where we already had two records, and now we want to execute our DBT project at t now, and we have the two timestamps from the previous run and the current timestamps. When we extract these timestamps and identify the corresponding Iceberg snapshot ID for the start snapshot ID and the end snapshot ID, we are able to load the original table inventory from the up to start snapshot ID. Let's call that data frame inventory, and anything delta which is added after that start snapshot ID up till now, let's call that an inventory delta data frame. And similarly, we can also load the prices table as prices data frame and prices delta data frame. And we can create temporary views out of it in our Spark session. And now the incremental maintenance SQL that we originally generated in terms of inventory delta, prices, and prices delta can directly be applied on top of those temporary views that we have just created. And the response of that can be appended to our original output table. And this will allow our output table at T1 timestamp with a single record to go to the right-hand side representation at T2 record, where we are only appending the data instead of dropping it and recomputing the previously existing record as well. So let's look at a quick demo to see this in action. Can you still see my screen?
Yeah.
Awesome. So on the left-hand side, I have a Spark shell open, and on the right-hand side, I have my DBT project where I have defined my models, and I would be executing a run for my DBT model. So on the left-hand side, as you can see, I have two tables, TBL1 and TBL2, both with one record each. And I have an output table simple join between two tables where I have computed a join between the tables TBL1 and TBL2. At this point, my output table has one record as expected, and this is my initial state of the project. Now, as I update my base tables TBL1 and TBL2 to add an additional record into each table, we'll see that our output table, simple join between two tables, needs to be refreshed. And we'll demonstrate how we can refresh that using the incremental maintenance mode. So let's query both of our tables to just validate the current state of the tables. So our TBL1 and TBL2 both have two records with two member IDs 123 and member ID 456. And we see in the output table, we only have one record for the member ID 123. So on the right-hand side, now let's look at our model, which has been defined using the incremental maintenance expected user experience and the SQL that we want to execute, which is the join between table 1 and table 2 on the member ID field. And now we can execute this DBT model just like we would execute for any other DBT provided configuration. And we can see it's first connecting to an adapter to integrate with the compute engine. We've implemented the Spark adapter to integrate with Spark compute engine. And right now it's trying to connect to Coral service to get an incremental SQL and then generate all the post-processing logic that we would run to create temporary views for all our 4 expected representations. And then we will just see that in a minute. Okay, as we see, it is finished successfully. And from the logs on the right-hand side, we can see that it was first able to query the snapshots of both data sets to extract the start snapshot ID and the end snapshot ID. And then it was able to load data up till the start snapshot ID in a temporary data frame TBL1 and TBL2. And it was also able to load the delta data added to both tables in the table underscore delta temporary views. And at the end of it, we see the query which was returned by Coral service, which is an incremental query defined in terms of those posts in those 4 data frames. And this was run to append to the table. On the left-hand side, we see that the output table has now been refreshed, and it has the additional member ID also available, which wasn't present previously. That's what I had for the demo. So there we have it. We have a desirable user experience where we have provided an end-to-end framework which will allow you to frequently and efficiently update your output models. The 2 main advantages of this framework are the low friction adoption. With the end-to-end framework, in a matter of 4 to 5 steps, you can set up your DBT project with this incremental maintenance materialization mode to actually efficiently update your system, to efficiently update your output data sets. So what are the next steps? At this point, we have demonstrated joins, and we've enabled efficient incremental maintenance for inner joins, and we want to extend the supported use cases and also enable it for aggregates and outer joins and other more complex queries. We also saw that the current support is for any additions to the base table. So for any additions, we compute the incremental table data to be added to the output table, but there can be other type of updates to the table, such as any record can get deleted, and the incremental SQL for that would look a little bit different, and that's what we want to enable the support for. And the third and equally important is to build a cost-based model, which will help us identify the optimal incremental plan. So for any given query, it's possible to have multiple incremental plans, and we should be able to evaluate the multiple plans and identify the right one to actually return to the user. So here I have linked the projects Coral and the Coral DBT submodule in the same project, where we have implemented the incremental maintenance materialization mode. And the Coral IR rewrite logic is in another submodule called Coral Incremental. There are README files in the projects which have clearly described the steps you would need to follow to import the materialization mode in your DBT project. And I would like to thank the LinkedIn team for tirelessly working on this project and to make it happen. And that would be all for the presentation. Thank you.
Thank you so much, Wal and Asta. That's fantastic. So I'd now like to open it up to questions from our audience. And we do only have 3 minutes, so they're going to have to be maybe just one question and a quick response. I'll go for one that's got 2 thumbs up here. It says, do you handle outer join in materialized views?
Yeah, so that question was answered in the future work slide, so no.
Yeah, okay, sorry, I missed that. And so have you looked at using SQL Glot instead of Coral?
Yeah, so Coral was actually like created at LinkedIn, and I think the main difference is that SQL Glot works at the AST layer more, and what we need for this type of rewrite is the logical plan, and that's one component that would be missing from SQL Glot for this use case. The other one would be the conversion from that IR back to the SQL, because we need this kind of conversion to enable having this rewrite happen outside the engine. So yes, we have looked, and there are a couple gaps there.
Thank you. There's one here, incremental query is fed to Spark, so Spark will optimize it. What addition optimization do you need?
Incremental query is fed to Spark, so Spark will optimize it. Well, Spark would execute the batch query if the batch query is fed to Spark. The point of this work is to convert the batch query to an incremental query and then feed the incremental query to Spark. So I'm not quite following the main point in the question.
Okay, that's fine. We can go on to, I think we've got one last one. Is there a plan to include Coral as the common representation for SQL within Iceberg for Iceberg views?
There is no active discussion at the moment. No.
Okay, fantastic. Well, I think with 1 minute to go, I think we'll wrap up there. So thank you.
I would like to address Julian's question too. So
Yeah,
in terms of the number of unions or joins, I think that is also part of the cost-based query optimization. So one of the options in cost-based optimization is not to do incremental at all. So based on that model, we can decide whether whatever like multiple part small join is more efficient, or just like one big large join would be more efficient. So
great. Thank you. So thank you for joining us, everyone. And thank you to Wal and Asta for a great session.